In this video, we're going to look at applications of integration, and specifically we're going to talk about displacement, velocity, and acceleration. So let's talk about displacement first. We could represent displacement by S of t, particularly if we were talking about displacement horizontally, you might do that, or you might represent displacement by h of t and call that the height. We'll see both situations in various examples in this video. Now, if we take the derivative of displacement, what we get is the velocity, call that v of t. And if we take the derivative of velocity, then we get acceleration, a of t. So if we lay out the three functions, displacement, velocity, and acceleration in this order, then we could say when we move this way, what we're doing is taking the derivative. And when we move this way, what we're doing is integrating. So if we say this in terms of formulas, we could say v of t is the derivative of s of t. Or if you want to say that more quickly, you could just say v equals s prime. So velocity is the derivative of displacement. You could say acceleration is the derivative of velocity. You could also say acceleration is the second derivative of displacement. We could say velocity is the integral of acceleration. So if you integrate acceleration with respect to time, you get velocity. You could say displacement is the integral of velocity. So if you integrate velocity with respect to time, you get your displacement. So let's try some examples involving displacement, velocity, and acceleration. A ball is thrown straight up from the ground with initial velocity 3 meters per second. Let's find the height h of t. So when the problem says find the height h of t, what this means is find a formula for the height at any point in time. So I'll just draw a little picture here. So the ball is starting at the ground, it's going straight up and then coming straight back down over the course of the problem. Well, our starting point in these type of problems where we've got vertical motion is going to be acceleration. We know that acceleration due to gravity is negative 9.8 meters per second squared. So we'll just say negative 9.8. Negative because we're talking in the downwards direction. So we're going to use the upwards direction as positive, downwards direction as negative, and that's conventional for all of these vertical displacement problems. Now, if we wanted velocity, then what we would do is integrate our acceleration with respect to time. So we'll say velocity is the integral of negative 9.8. Don't really need brackets on there because we've just got a single term in there. So let's do our integration. So negative 9.8 is constant. When we integrate, it becomes negative 9.8 times t plus some constant c. Remember that with these indefinite integrals, you always need plus a constant. Okay, now let's see if we have enough information in the problem to actually solve for c. We know the ball's initial velocity. We're told the initial velocity is 3 meters per second. So what that means is that velocity is equal to 3 when time is equal to 0. Time equals 0 just being the start of the problem. So let's sub that in and see if we can get more information about v. So we're saying 3 equals 0 plus c. In other words, c equals 3. And so what I'm going to get in the habit of doing is every time I figure out what the function is, I'm going to put it in a box like this. And then that way, if there's a follow-up discussion about the value of the constant, then we know we're just plugging back into that box. So here we're going to come up with a new and improved version of our velocity function. Now we know it's negative 9.8 t plus 3. So we'll put that in a box there. Okay, so that's our velocity function. And now we want to do this process of integrating one more time to try to find the height. So when you integrate velocity, you're getting position. You could call that position s, particularly if you're doing a problem in horizontal motion, you might call it s. But if you're doing a problem involving vertical motion, more natural to call that h. So this is going to be our height, and we're going to get that by integrating velocity with respect to time. So if at any point you find yourself confused about how all these functions are related, you can always do units analysis. Height is going to be measured in meters. Velocity would be measured in meters per second. And a dt here represents a tiny chunk of time, so that's measured in seconds. So then you can convince yourself, yeah, when I multiply meters per second times seconds, I do actually get meters. So let's go ahead and integrate our velocity function. We're going to integrate negative 9.8t plus 3, integrate that with respect to t, and that's going to give us our height. So we're going to have negative 9.8 t squared over 2 plus 3t plus some constant. Now this constant here, we really should not call it c because we've already used c earlier in the problem. So you can call that capital D if you want, or you could get into the habit of calling the first one C1 and calling the second one C2. So you can use pretty much whatever naming convention you want, as long as you're using different names for your constants. All right, now let's see what we know about our height, because we should be able to figure out the value of D. I'm going to put this height function in a box so that we can come back to that quickly when we need to plug into it. So let's scroll back to our problem. What do we know about the ball? We know it's thrown straight up from the ground. So the fact that it's starting on the ground actually gives us our initial height. That's telling us that at time 0, the height of the ball was 0. So we'll sub that in, and that's going to give us D. So we're saying 0 equals 0 plus 0 plus D. In other words, D has to equal 0. So we can take that, plug that in, and we're going to have our final answer coming up in the next step. So for this final answer, you can do any simplifying that you want. For example, you might take that 9.8 and just divide it by 2. So that first term becomes negative 4.9 t squared plus 3t, and we figured out that d is 0. So this is the formula for the height that we're looking for. So now that we have that formula, we can predict what the height of the ball would be at any point in time. For our next problem, a ball is thrown straight up from 12 meters high. It takes 6 seconds to land. Find h of t and the initial velocity v0. Okay, there was a picture in the notes. I've just erased it so that I can redraw the picture fresh. So this ball is not starting on the ground. It's starting from 12 meters high. Okay, so let's say that's a height of 12 meters above the ground. So it's going to go straight up for some time, and then it's going to come straight back down, all the way down to the ground. So let's start at the same starting point as our previous problem. Anytime you've got vertical motion, you can start with acceleration due to gravity. We'll say the negative direction is downwards, so acceleration negative 9.8 meters per second squared. And let's go ahead and find a formula for velocity just by integrating our acceleration function. All right, so let's integrate our acceleration. We're just integrating negative 9.8 with respect to t. So that tells us that velocity is equal to negative 9.8 t plus some constant. So I'm going to call this constant C1 because we'll likely have another constant later in the problem. Okay, now let's look back at the problem and see if we knew our initial velocity or any information about our velocity. No, but one piece of notation we were told is that we're going to call the initial velocity v0. Okay, so let's do that. Let's say that at time 0, our velocity is v0, or v0, you could call that. So that's not going to give us a numerical value, but it will give us a nice intuitive notation. So v gets replaced with v0, time is 0. So in other words, we're just getting the value of c1. We're saying c1 represents that initial velocity. So let's sub that in. We'll get a new and improved version of our velocity function. So it's negative 9.8t plus v0. So we'll put that in a box. All right, now if we do one more step of integration, then we get height. Height is going to be the integral of velocity with respect to time. So h is going to be the integral of negative 9.8t plus v0 integrated with respect to t. So in other words, h becomes negative 9.8 t squared over 2. So I'm going to get in the habit of just simplifying coefficients as we go. So negative 4.9 t squared plus, continuing to integrate, this v0 is a constant. So when we integrate, we get v0 times t, and then plus some constant, which let's call that c2. We already used the name c1 earlier in the problem, we use that up here. So this constant has to be given a different name because in general, its value will not be the same as C1 that we saw earlier. So let's see if we've got any information to help us find C2. And what might be good here is just to put our height function in a box so that it's easy to come back to if we need to sub in. Okay, so what have we used? The ball is thrown straight up. Yep, from 12 meters high. Okay, that's what we're going to use here. And also it takes 6 seconds to land. Okay, we'll keep this in mind. We'll likely use that towards the end of the problem. Find h of t and the initial velocity v0. Okay, so let's use the fact that this ball is starting from 12 meters high. So at time 0, height is 12. So 12 is equal to 0 plus 0 plus c2. In other words, c2 is 0. Or sorry, c2 is 12 is what we figured out there. So let's sub that in and we get our formula for h. So h is negative 4.9 t squared plus this mystery v0 times t plus 12. So this is actually half of our final answer. The problem was asking us to, first of all, find a formula for h. So we've done that. And then second part of the problem was to find v0. So let's see what we can use to get that second piece of the answer. So we've used the 12 meters high. It takes 6 seconds to land. So let's see what we can do with that. So when the ball lands, at the moment that the ball lands, the height is 0. So we're saying height is 0 at time 6 seconds. All right, so let's sub that in, and that's in fact going to give us the v0 that we need to finish the problem. So 0 equals negative 4.9 times, subbing in t equals 6, this is going to be 36, plus this will be 6 times v0 plus 12. Okay, sure enough, we've got a little equation that we can solve for v0. So let's just bring two of the terms over to the left side. So 4.9 times 36 minus 12 is equal to 6v0, and then we can divide that whole expression on the left side by 6. So if you're going to do this on your calculator, just remember you'd need brackets around the whole left side when you divide by 6 there. Comes out to 27.4 meters per second. And I'll just put a check mark here to show that's the second half of our answer. So our answer really involved two things. One was finding this formula for the height, done. And second was, once we had that, to figure out what our actual initial velocity was, 27.4 meters per second. So next problem we're going to do will involve displacement in the horizontal direction. So next problem, we're told that a car travels in a straight line with a given acceleration. Notice that the acceleration is negative, so that means the car is actually decelerating or slowing down, you could say. The brakes are applied when the velocity equals 20 meters per second, and we want to find the stopping distance. So let's start with acceleration. We'll just copy it as it was given in the problem, negative 4t. Velocity will be the integral of acceleration. So that means velocity is going to be, well, you could say negative 4t squared over 2, but I'd be inclined just to simplify the coefficient there and make that minus 2t squared plus some constant. So let's say plus c1. Let's see what we know about our initial velocity. And I just get in the habit of crossing out stuff once we've used it. So the car travels in a straight line. Okay, we've used the acceleration. The brakes are applied when the velocity is equal to 20 meters per second. So let's say this. Often it's a good idea just to introduce a coordinate system. And in this problem, that means saying what time 0 represents. So let's say time 0, the moment when the clock starts, is when the brakes are applied. And we're going to write down some facts that we know about that moment in time. So we know that the velocity at that point is 20 meters per second. So I would phrase that as v of 0 is equal to 20. I'm just going to keep this box here. I think we will come back to it a little bit later in the problem, but for now we're going to use the fact that v0 is equal to 20. So we're going to sub in v equal 20 and time 0. And that's going to give us our value of c1. So we'll put this stuff in a box. Okay, so 20 is equal to 0 plus c1. In other words, c1 is equal to 20, we can sub that in and just get a new and improved version of our velocity function. So velocity is equal to negative 2t squared plus 20. Okay, so now the question is, what is the stopping distance? So let's think through, just from a logical point of view, what we would need to do that. So some of the things we're going to need to do. Well, we'll need to find our displacement function for sure. So we'll need to get s. And then if you think about how we would calculate a stopping distance, we would actually need to know the stopping time. And then once we had a stopping time, then we could plug that stopping time into our displacement function, because the displacement function accepts a time value and then it puts out an amount of displacement. So it takes in a number of seconds and puts out a number of meters. So we'd need the stopping time, and then from there we could get the stopping distance. Really, we could do these things in either order. We could figure out the stopping time right now, and then we could deal with the displacement function, or we could deal with the displacement function now and then do the stopping time later. It doesn't really matter. I think since we're kind of in this groove of integrating, let's go ahead and figure out our displacement function. Displacement, I'm going to call this S because this car is moving horizontally as opposed to vertically. S is going to be the integral of velocity with respect to time. So specifically, it's going to be the integral of negative 2t squared plus 20 with respect to t. And let's do our integration. So this is going to be negative 2t cubed over 3 plus 20t plus some constant. So I'm going to call this C2, and the thing to keep in mind is just that you want to give it a different name than the constant that you used for velocity. There's no reason that those two would be the same number, so they need different names. All right, and then let's see what we know about displacement, because we want to figure out this value of C2 and get a finalized displacement function. So what I'm going to do is put this stuff in a box. We're going to come back to it in a minute once we figure out the value of C2. So let's come back to this box that we were talking about up at the top of the problem. We said we introduced a coordinate system, and what that means is really just talking about the interpretation or the physical interpretation of time zero. So time zero is the moment that the brakes are applied. Let's think about what that means for displacement. So S here is representing our displacement function. And if you write down a definition of what displacement is, it is how far the object has moved from its starting point. So this is actually an important distinction between displacement and position. Sometimes people use those terms interchangeably, but they're really not interchangeable. Position is like if you have an x-axis or something like that, and someone says, okay, you're starting at x equal 3. That's your position. But displacement is a little bit different. It's specifically measured with respect to an object's starting point. So if you keep that definition in mind, then S of 0 must be 0, because by definition, at time 0, at the moment that the problem starts, how far has the object moved from its starting point? Well, it hasn't moved yet. That is a bit of a subtlety. It's something that can easily trip people up because it's something that's implied and not stated in the problem. But that's actually what we're going to use right now to find the value of C2. So we're going to say, since this S represents displacement, then by definition, at the start of the problem, which is when the brakes are applied, the object has not moved any distance from where it was when the brakes were applied. So its displacement is 0. Okay, so subbing in 0 equals 0 plus C2, which means C2 just has the value 0. And we can sub that in here and get a nice displacement function. So here's our finalized displacement function. S is equal to negative 2t cubed over 3 plus 20t. So what I'm going to do at this point is highlight our finalized displacement function, because we're going to need that. And the other thing we're going to need is our finalized velocity function. So that's right here. So if you wanted to break this problem into steps, I would say first step is to find your acceleration, your velocity, and your displacement. So we've done that. And then, as we mentioned, we're going to need to figure out the stopping time. And then once we've got that, then we can figure out the stopping distance. So we simply cannot figure out the stopping distance without knowing how long it takes to stop. So I'll just label this part step 1. I've recopied the displacement and the velocity functions from our previous page. And now we're going to figure out the stopping time. So how long does it take the car to stop? Well, let's think about the moment that the car stops. What do we know? We know its velocity is 0. That's just the definition of stopped. The car is not moving. So if we sub in v equals 0 into our velocity function, that's going to give us the time that it takes the car to stop. So let's try that. 0 equals negative 2t squared plus 20. In other words, 2t squared is equal to 20. T squared is equal to 10. And that actually gives us two different solutions. T could be either plus or minus root 10. But because we're dealing with a physical problem, we know time is going to be positive. We can then immediately say, okay, that means root 10. So it takes root 10 seconds for this car to stop. Okay, and then phase 3 of the problem, this is where we're going to get our final answer. We're going to do our stopping distance. Okay, so if we want distance, then that's going to mean using the displacement function. So negative 2t cubed over 3 plus 20t. We want to figure out what the displacement is at the moment that the car stops. And what needs to get subbed into this is a time value. So that's why we had to find our stopping time in step 2. We figured out that the stopping time is t equal root 10. So if we plug that stopping time into displacement, what we get is our stopping distance. This is s of root 10 that we're calculating here. What we're going to sub into our calculator, negative 2 times root 10 cubed over 3 plus 20 times root 10. We'll have our final answer coming up here. So it's about 42.2 meters for stopping distance. So here's our last problem. We've got a helicopter and we're told that the angular velocity of the rotor is given by this. So just a point on notation here, we're going to let theta be the angular displacement. And therefore, if you take the derivative of that with respect to time, what you get is angular velocity. And what we want to do is find the angular displacement, which we'll call theta or theta of t, after 5 seconds. So that's going to help us figure out how many rotations has this rotor gone through in the first 5 seconds of the problem. Well, remember that if you want to move from velocity to displacement, then what you need to do is integrate. And that's true whether you're talking about regular velocity or angular velocity. So let's see if we can come up with a formula for how to write that down. If we want to figure out our angular displacement, we need to integrate angular velocity. So we need to take the integral of d theta by dt, and we are integrating with respect to t. You can just convince yourself that the units work out here because theta, your angular displacement, is going to be something like measured in radians. And d theta by dt is going to be like radians per second. dt is a little chunk of time, so that's measured in seconds. So yeah, the units work out. If you multiply these two on the right, you do really get back to radians. Okay, so let's plug in what d theta by dt is. It is the square root of a cube. So I might just call that something raised to the power 3/2. It's 4t plus 1 to the 3/2. And that needs to get integrated with respect to t. All right, now this is going to be a bit of a multi-concept problem because we actually need to do a substitution here to get this integral figured out. So let's substitute the quantity that's being raised to a power, which would be 4t plus 1. du by dt would be equal to 4. So in other words, du is equal to 4 dt. And if we look back up at our integral, we don't have a 4 dt, we just have a dt. So du over 4 is going to be the same thing as dt. Keeping in mind that u is 4t plus 1 and that dt is du over 4, let's see if we can rewrite this integral. So we're saying theta is equal to the integral of u to the 3/2 times the dt becomes a du over 4, and we would just put the 1/4 out in front. Okay, so that's great. We've accomplished our substitution, and now we can go ahead with the integration. So the 1/4 will hang out in front. We will bump up the power on the u to make it u to the 5/2, divide by that new power, and then we need to say plus a constant, so plus c. Okay, now we're going to do some further calculation with this, so let's just clean this up a tiny bit. The coefficients here can be simplified. Instead of saying 2 over 20, let's say 1 over 10. And instead of saying u, we really should go back to our original variable. U is 4t plus 1, so we'll sub that in, and then plus some constant. So this is a formula for our angular displacement. How many radians of rotation have those rotors gone through since we started the clock? Initial displacement is equal to 0. Okay, so why is that true? Well, that has to do with the definition of displacement. Displacement is how far have you moved from your starting point. So at the start of the problem, we have not moved any distance from our starting point. So initial displacement is always 0. If you're calling your displacement s, then that's written as s of 0 equals 0. But in this problem, we're using slightly different notation. We're not calling our displacement s, we're calling it theta. So theta of 0 is equal to 0. All right, so let's sub that in, meaning we're subbing in theta equals 0 when time equals 0. So subbing in that combination is going to give us our c value. Okay, so 0 is equal to 1/10 times, subbing in t equals 0, we get 1 to the 5/2 plus c. So in other words, this whole first term here is just 1/10. So if we move that over to the other side, that's minus 1/10 is equal to c. And let's sub that in. So subbing that in to our equation up here, we're going to get our nice displacement function, our angular displacement. So theta is equal to 1/10 of 4t plus 1 raised to the power 5/2 minus 1/10. So if the problem were just asking find a formula for the angular displacement, we would be done. Always good to go back and just figure out what the question is asking. So the problem is to find the angular displacement after 5 seconds. Okay, so here we go. We're going to sub in t equal 5 and we'll have our answer. So theta is equal to 1/10 of, subbing in t equal 5, we're going to have 21 to the 5/2 minus 1 over 10. And you can put that into your calculator and just figure out roughly what that comes out to. So it comes out to about 201.99. So theta is an amount of rotation. In other words, it's an angle. And this is going to be measured in radians. So 201.99 radians, that's how much rotation the rotors have gone through. So what might be more physically meaningful here is if we just convert this to a number of rotations. So what we would need to do is just divide by 2 pi, or if you wanted to think about this just in terms of proper units, you could say multiply it by 1 over 2 pi, because you're really saying 1 rotation per 2 pi radians. And that would take you into a number of rotations. So dividing 201.99 by 2 pi comes out to about 32. Okay, so to me that's more intuitive. So this rotor has gone through about 32 full rotations in the first 5 seconds. So that's our video on displacement, velocity, and acceleration. Thanks for watching.